Lab 2 of Physics 2211, projectile motion. So to start, introduction and purpose. The purposes are to analyze real projectile motion using video tracking, to model projectile motion using Newton's second law, a gravity-only model, and a gravity plus drag model, and to compare experimental data to physics predictions. Preview of the main result. Gravity-only model predicts too large a range. Gravity plus drag model best matches the experimental data, and the experimental trajectory is slightly asymmetric, likely due to throw variations. Physics principles and models, the system and surroundings. The system is the marker, which is the thrown object, with a mass of 0.0115 kilograms. Surroundings are Earth, which has gravity, and air, which has drag. And then the physics that are used to calculate in this lab are Newton's second law, the position update formula, the velocity update formula, and force of gravity and force of drag. The experimental setup, the initial conditions are the initial position is 6.625 off of the ground, mass of the marker, and then the force of gravity is 9.8 meters per second squared. The origin is right beneath the marker on the table, and that's the calibration setup. The tracker data, these are the graphs that tracker gave. The horizontal displacement at the end was 0.658 meters. The vertical displacement is 0.6 meters. Maximum height is 0.625 meters, and the trajectory curve is slightly asymmetric. The gravity-only computational model, the code on the right stays the same throughout the entire process, but the code on the left, the only change made is the B value. For this one, the B value is 0 because there is no drag. The net force is F net equals mg in this case. There's no horizontal force. There's constant downward acceleration of negative 9.8. The final x position is negative 0.520 meters. Final y is negative 0.522 meters with a perfect parabolic trajectory. For the gravity drag computational model, the only thing that changes is the B value is now 0.032, which is solved using the calculations to the left of the code. The net force in this case is F net equals mg plus F drag. Drag always opposes velocity. The magnitude is proportional to speed squared, and the drag coefficient B is adjusted to match the data. The final x is negative 0.222 meters, and the final y is negative 0.022 meters. The trajectory is less steep than the gravity-only model. Experimental versus model trajectories. On the graph to the left, the yellow line is the with drag, the blue line is no drag, and the red dots are the tracker data. Tracker final position was x equals 0.4 and y equals 0.01, both in meters. The gravity only overshoots horizontally and overshoots vertically. The drag model is closer to the experimental landing point. Experimental path is slightly asymmetric, and air resistance affects both x and y motion. Does the object reach terminal velocity? Terminal velocity is when net force equals 0, meaning it occurs with F drag equals the force of gravity. Gravity only model is no. Gravity drag model is the drag increases with speed, but still no. The flight time is too short to reach terminal velocity. If you wanted to reach terminal velocity, you have to drop the object from a greater height and measure until velocity versus time is constant. What if the object was thrown straight up? Same initial speed, all velocities in the vertical direction. However, the flight time would be the flight time is t equals 2v naught divided by g. It'd be a larger vertical displacement. The time to hit the ground would be longer, and with drag, it's even longer than the ideal prediction. Source of experimental error could be camera not perfectly perpendicular, calimetric stick, could be uncertain, frame rate limitations, slice initial variations. In throw, approximated drag coefficient B could be slightly off, and air currents in the room. Conclusions, projectile motion governed by Newton's second law. Gravity-only model predicts the ideal parabola. Experimental drag deviates from the ideal model. Drag gets closer to the actual result. Air resistance is significant in real motion, and computational modeling validates physical assumptions.